Hi, good afternoon, everyone. I'm Prasad from
Today.
Merck, India. Good afternoon. I hope each one of you is staying safe and healthy. Our material science portfolio includes the most advanced quality tested products for material synthesis as well as other products from material science such as energy, biomedical, electronics, and material synthesis. Welcome to today's webinar on polymers. Not It's a solution, not the problem, and it will be conducted by our partner Goodfellow from UK. Goodfellow is well known as a specialist supplier of metals, alloys, ceramics, polymers, and other materials to meet the research, development, and specialist production requirement of science and industry worldwide. So I thank my colleague Dr. Rama, Dr. Milind, and Chirag, as well as our IT colleagues from India, and Simon, Dr. Aphrodite from Goodfellow for helping us hosting this webinar today. Our speaker for today is Paul Everett. Paul is a technical support specialist at Goodfellow Cambridge Limited with a broad range of materials knowledge, particularly in the field of polymers and composites. Previous experience includes the plastic stocks step sector, manufacturing, automotive account management, condition monitoring equipment, business development, safety data sheet authoring, and most recently in technical supports role. Paul holds a BA in Polymer Engineering from London Metropolitan University and a master's degree in Advanced Materials Technology from University of Surrey. Enjoy the presentation. We would like to have your questions. Please type the questions at the panel. We would answer your questions toward the end of the presentation. If due to some time constraints we are unable to answer all the questions during the session, please be assured that we will send across those questions to Goodfellow team and get you the answer. For a better connectivity to the session, please allow low bandwidth mode from bottom right setting tab on your screen. That's all from me. I now hand over the polymers, the solution, not the problem session to Paul. Over to you, Paul.
Thank you. This is where I try and get everything working. And how do I do the screen share? Bear with a second, just trying to get to share my screen. Good. Right, good afternoon. Thank you for the introduction. So my name is Paul Everett. I've been with Goodfellow for very fast approaching 19 years, so I have a bit of experience of not just the polymer range and composites, but a reasonably broad base across all of the materials and a number of other aspects including things like safety data sheet authoring. I think I've got a bit of a background. Today we're going to briefly look at some polymers. What are they? Polyimide Film, which is one of our big selling products, polyesters, PEEK, a PHB, and then we'll sort of wrap up with a sort of suggestion about sales growth for future and how hopefully we use this as an opportunity to open a dialogue and kind of exchange ideas, because we're always learning and we're always wanting to hear from our customers what their particular market is looking for. So let's just start off with Goodfellow. We've already explained that Goodfellow has been providing materials to research community and specialist manufacturing for over 70 years now. We started off as a bulk metals distributor, and over time sort of morphed into the current model where we source the product in larger volumes and break them down into smaller lots for people to try. Because some of the big challenges we're seeing today are about increasing minimum order quantities from manufacturers, which make it very difficult when you want to simply try something. You know, you can model, you can design things, but sometimes you actually need product in your hand to simply see what it does and how it behaves. Now, polymers, my background goes back to many years. back into the 1980s when I started working in what they call the stock shape sector, where you're manufacturing rods and tubes and sheets. And I've got somebody knocking at the window. Gone. Postman. One of the joys of working from home. Polymers are basically long chain molecules made up by small repeat units or monomers, which go through a polymerization process to create a long chain. Now, there are other materials that are not plastics that are polymers, things like DNA. You've probably seen the long chain molecules of a DNA, and plastics are similar in that you've got that long scale. So it can be many thousands of units. You can go right up to many millions in the case of ultra-high molecular weight polyethylene. The example I've shown here on the right-hand side is that of polypropylene, where you can see the carbon and hydrogen atoms, and this is the monomer or the repeat unit, and then how you've got side branching, which is the CH3s coming off here. Quite a relatively rigid, but also for a lot of plastics quite flexible. So I like to think of them as like the building blocks being the monomers, so little blocks of Lego, and you add them together and get longer and longer chains to get your polymer. Now, I've grown up over, say, many years seeing a number of these performance pyramids, and you find some organisations will tend to focus on a particular area within the performance pyramid. So you have people who will perhaps work with the commodity materials. So if you're making conveyors, packaging, engineering materials, so if you're wanting gears and things with mechanical performance, and then move up into what we term the high temperature or high performance materials, where you've got melt temperatures going up and up and up, and in fact you get to polyimides, PBI, which are actually thermosets, so they don't actually melt. We tend, or we try to cover this entire pyramid, which can be a challenge because you cannot be a specialist in all of these areas, but we do try. But we'll go through some of these materials in a little bit of detail, but the time is time permitting, and answer any questions as we go. When you look at plastics or polymers, you have to think about the structure-property relationship. In the case of an amorphous polymer, where there is virtually no order, you've got a completely random product, we'll go through heating, which will cause it to expand, create extra free space between the polymer chains, and then upon cooling, it will contract and solidify. The key temperature with amorphous materials to bear in mind is the glass transition temperature, which I can unashamedly say has been ripped off from the glass manufacturing people. It's the point at which the polymer goes from being hard glassy state to a soft ductile one where you can actually shape and form it. Semi-crystalline materials, as you can see, there's some regions of order interconnected with these amorphous regions. However, when you process that material, if you increase the temperature to the point where all of the order disappears and it becomes an amorphous material, and then as you cool, you start to find that the crystals, polymer crystals, unlike metallics, or the regions of order will start to form again, and you then have this structure of bits of amorphous sections and the crystalline bits. In theory, you cannot get 100% crystalline polymer. Now, the temperature that dominates with semi-crystalline materials is their melt temperature. So you can see these regions are quite important in the overall strength, depending on the working temperature of the material. Further product to briefly mention is a liquid crystalline polymer, where if you actually look at this, it's almost like the structure of wood. So you have the polymer chains are highly aligned, go through the melting process, and they stay aligned, which gives you materials with really high strength. But across the chains, you have problems with fracture along these lines. So they're very directional in terms of their strength. So finally, we've got thermosets, which, as the name suggests, actually set during a heating process, which could cause a chemical reaction, cross-linking, and whatever you do to this product, it's amorphous. You cannot reshape, you cannot effectively remelt it. You could recycle by breaking it down and using it as perhaps additives or fillers in other products. Then we look at some of the changes or the differences between the two. So we say thermoplastics can be remelted and recycled, whereas thermosets undergo a one-time chemical reaction and cannot be remelted or traditionally recycled. Although I know a lot of work is going on in chemically recycling these materials. Thermosets generally are harder and much more brittle than thermoplastics. And I've given some examples of the materials that you can find in our range, going from common or garden polyamides. We'll talk about PET later. We've got PEEK, and then Kapton, which is a very important product for us. And some of the thermosetting materials you'll find in the home around you, kitchen work surfaces, phenolics, which are used as adhesives and also lacquers. And then if you look at composites, there's the epoxies and vinyl esters. And vinyl esters, the advantage over epoxy, gives you much better surface finishes. So a glossy appearance tends to be what you'll see with a vinyl ester. Okay. Now, when we look at polymers, and we hear the bad press about how they're supposedly causing issues with the environment, and yes, there are problems, and that's all around really our treatment of them at their end of use. But they can certainly assist by having a lower density. Now, if you compare, they put PET with a glass bottle. In Germany, there has been great strides in recycling of PET bottles, and particularly in the adoption for beer, for instance, and having recycling rewards, basically. So you get some money back on those bottles. It's cheaper to transport them because of the weight change compared to glass, which also for the environment is good, because that means you're shipping less weight, so lower emissions. They're also becoming increasingly available from sustainable sources. So you've probably seen, or in food packaging, a product called PLA, polylactic acid, which can be recycled, but also is mostly compostable in industrial composting equipment. You also see that generally biopolymers can be composted. So PHB, which we'll talk about later, you could actually place that in your garden waste and it would degrade very much at the rate of, say, for instance, wood, and can be used to go back into the soil and act as a fertilizer. Also, if you think about polymers and the way that they're produced, they're relatively low temperature melts. If you compare that with the metallics of, say, steels, say titanium, it's lower cost to make product from a polymer than it is from a metal, but also ease of manufacture. I've got a nice little example of an Arberg all-rounder. There are other processing machinery suppliers available in the marketplace, but my experience with Arberg has been that they're very user-friendly machines, very nice to use, and also fairly low cost of maintenance and low electrical costs. So you're talking about advantage of, again, you're helping to save electricity and the environment, and as a sort of side effect. Now, if we look at some of the sectors that we've been engaging with over the years and seen kind of quite big strides forward in terms of the electronics industry. We all have, well, most people have these days, these smartphones, where increasingly you're wanting more and more processing capability within the device, and also probably seeing flexible screens. Now, the only way you can achieve these advanced or gains in these sort of equipment is by the use of plastics, particularly in substrates, and I think there's a good example here of a printed flexible substrate on the top right hand side. Things like even the rigid substrates, where you're looking at perhaps higher and higher operating temperatures because of the density of the electronics, the amount of power they consume. And in fact, if you think about your processing power within, say, an iPhone, how that has gained over many years of development. So it's quite an important area going forwards. Another area which I have some personal experience from is automotive. And even with the internal combustion engine, there have been opportunities for weight reduction that have been exploited with the adoption of polymers. But if you look at now the new electric vehicles, and friends of ours have a BMW, which doesn't look too different to this interior trim. There are lots of screens around their vehicle, and again, mostly only achievable from having polymers within the device, or the vehicle. Another area that you might consider that could be coming through would be, what about the capability using your processing power that you have in your vehicle, combine that with sensors within the vehicle, monitoring air condition, maybe even monitoring the health of the driver. I know that sounds probably a little outlandish, but with all that processing power sitting there whilst you're driving and an opportunity to monitor the driver, there could well be opportunities for even greater growth into electronics within automotive. Any questions, anybody so far? Okay, so I'm moving on. Okay, further sectors that we can look at are, as I say, we've talked about mobile diagnostics. We've looked at the sensors, and I've been to a number of conferences where they've discussed the rollout of all sorts of sensors that are based on monitoring, say, for instance, the chemistry of your blood, and also things like blood sugar levels, glucose, etc. So if you can link these flexible printed sensors to maybe your mobile phone with an app that alerts your clinician that you have an issue with a particular outstanding condition, then it could be used again to help speed up response of clinicians to an issue. An area that we've also seen huge interest, not just in the flexible circuit side, which is space satellites. We were involved in an application on the International Space Station some years ago for an acrylic light guide on an astrophysics experiment. Now, the obvious advantage with space is, that they are trying to come to cost reductions through using standard products rather than necessarily having materials produced specifically for space. The adoption of standard products obviously reduces cost. It has the advantage of the historic reliability of that product, and also going forwards, you can roll them out over the smaller and smaller sort of mini satellites that are being produced, and so the sort of constellation of small microsatellites that are being proposed will be cost effective and reliable, which also ties in with all of these areas of mobile technology and healthcare. And as we know in the current pandemic, exchange of data is critical to controlling the spread of disease. We're now going to have a quick look at Polyimide Kapton, particularly, which is a DuPont branded product. Now, the eagle-eyed people in the audience will see over to the left-hand side here the benzene rings that form the main backbone of polyimide, which means you have quite a strong material. I was just checking timings. Which in this case, the polyimide of Kapton is a thermoset. So once it's produced, you can't remelt it. Now, it's actually the biggest polymer stroke form that we sell globally, and has been growing quite rapidly over the last 4 years, and is currently second highest in India. As I say, it's an amorphous thermosetting polymer, and DuPont claim reliable and consistent film material, which actually, to be fair to them, is pretty accurate. Thin, light, and very tough and flexible. So printed circuits, its ability to basically in a thermoset means it won't melt. The worst that can happen is get charring. And it's also good, very good, in fact, in resisting high energy radiation. And so we see that in terms of space applications, very early days used in the Apollo moon missions, and in fact coated with gold, used as a thermal insulator on the moon lander. So it has some history, so to speak, in space exploration. But one of its key things is it keeps these properties over a very broad temperature range. If we move on, we'll see that, yeah, you've got UR94 RTI of 200 degrees C for mechanical and 240 for electrical. So you're looking at a really robust material that can operate across a very broad temperature range, which goes from the cryogenic, minus 269 degrees C, to 400, which is very few materials could offer that while staying flexible. The key temperature property or characteristic, we talked about glass transition temperature from 360 to 410 degrees C. That's phenomenally high for a polymer, and is really interesting. It has some drawbacks in terms of its resistance to certain chemicals, i.e. steam. So hydrolytic stability is not good, and also very strong alkali and very strong acid solutions. And it's also UR94 V0 rated, so and VTMO, which is even higher, depending on the type. So it does not catch fire. So it just doesn't burn. It will char. Is its way of degrading. We have, I could suggest, possibly the broadest range of grades available from stock. There are a number that we haven't adopted yet, but they are potentials for the future. Kapton HN, which is the basic grade, the unfilled grade, and I've included some images to show how the colour, which we're frequently asked about, can range from this sort of very pale amber through to very dark amber. We also have a grade called Kapton MT. Now, polymers in general have very poor thermal, transmission characteristics. They're very good thermal insulators, but if you, for instance, wanted a printed circuit where you wanted to conduct heat away, that can be a problem. So DuPont have this Kapton MT grade that has 3 times the thermal conductivity of HN, but also with the fillers they've put in there, you've got better cut through strength. So again, a more robust, flexible circuit, maybe in more demanding environments, you can use. And then Kapton CR. Now, a lot of polymers you may hear have been corona treated to aid bonding. Now, what you tend to do here is you're introducing oxygen species into the surface, which, although makes it possible to bond to the material, it also has an impact on the physical properties eventually over time. So with Kapton CR, it's been specially developed to overcome those problems of corona discharge. So in electrical switchgear, for instance. So again, more electrical insulation properties and longer lasting. So although relatively expensive compared to other materials, you get a lot longer life out of this. So not having to go out and maintain in the marketplace. Then we have a black polyimide, Kapton B, which is very similar to Kapton HN, with an even better balance of physical properties due to the additional fillers, and also able to operate at higher operating temperatures compared to the standard HN. Now, I'll show you when we have our next session, because I've actually got an example of the flexible circuit at the bottom there. And believe me, when you take a little battery and you connect it up, it does actually heat up quite rapidly, this little flexible heater. DuPont, we're talking about using these in aerospace to help defrost or aircraft, and you could actually create circuits. So you could say slit and print, and you can have a arrangement of these, not just the little rectangular sample you see here. Then there's another grade, again used in, as you can see, in heaters, that's been treated on both sides, so you can bond to it, and it also works over a wide temperature range and with better physical and chemical properties. And then a product called HPPST, which is low shrinkage. So again, a blend of fillers to help with the dimensional stability of Kapton, because even Kapton will shrink when you expose it to high temperatures. Some of the applications we see with Kapton, the printed circuits particularly, are a big increase in use in Kapton. In automotive, you can see with the insulators in various sensors, in X-ray windows, because you can pull a vacuum, because it's quite a strong material and it doesn't filter out X-rays so much in the low thicknesses. Thermal management in space applications, and we're seeing that in the current mission to Mars from NASA, and then the little flexible heater that we talked about just before. Now we can look at the biggest selling product, or polymer product, in India for us, and that's polyester film. And again, if you look at the structure of polyester, there is a benzene ring in there, which says you've got some pretty good chemical resistance properties. But also, if you look to the left-hand side, you have the CH2 repeat units, which are the effectively polyethylene bit. So you can see that polyester is actually a thermoplastic. There are a number of trade names you may have come across, including Mylar, Melanex, and Hostafan. They are DuPont and Mitsubishi polyester, respectively. We have a really, really good tie-up, or rather, with a relationship with DuPont Teijin, which has allowed us to get these films as low, as thin as 0.5 of a micron. Now, believe me, it's not easy to handle at that thickness, but we do know that people have used it successfully in things like X-ray windows. and various other applications where you want a very thin, very flexible, but also a barrier to gases, for instance, that you can pull a vacuum. And despite people talking about amorphous PET or APET, all commercially available polyester or PET is actually semi-crystalline. Now, that I found personally a bit bizarre, how the industry can call something amorphous when it isn't, but they claim that it's below 40%, they can call it amorphous. Excellent chemical resistance. It's very, very difficult to dissolve, so it's very difficult to characterize for, say, for instance, molecular weight, which is why you'll find very few people will publish that information, and generally the best you'll tend to find is intrinsic viscosity. We got that from the horse's mouth from DuPont Teijin, because the chemicals traditionally have been used in the past have been banned for a number of years because they're just pretty nasty. We have an operating temperature range, not quite in the realms of Kapton, but minus 60 to 170 degrees C, which, yeah, is pretty good. Even you think about food packaging, it has its place. There are a lot of choice. We have over 40 catalogue items, and as I said, molecular weight information isn't available. Hydrolytic stability isn't brilliant. You can sort of steam sterilize it maybe once, a couple of times maybe, but it will cause failure of the material as it breaks down. And a few examples of some of the products we cover: white printable films, opaque films. We've got heat sealable, peelable films that you find in food packaging. We chose this product particularly originally to support our own packaging requirements when we were vacuum forming trays and wanted to ship sensitive metallic materials in little blister packs, so to speak, and that proved to be quite a popular product, actually. We also have metallized films, so that, again, thermal management, both single and double side. And as you can see from the list over here, some of the applications through X-ray windows through to labels, identity cards, driving licenses, for example, and metallized films in food packaging as well, and capacitor films, where a lot of the very thin films came from. It's considering it's an engineering stroke commodity material, it's quite an interesting product, and I suggest we have even more areas for growth in the future. Another popular product, and one that we have seen a lot of growth in the last few years, and currently number 4 in the Indian leaderboard in the table. Again, you see to the right hand side here this time the benzene rings on the polymer chain. So you've got a rigid backbone, but as a thermoplastic you can actually remelt and you can reshape this material. Now we have a really good relationship with Victrex, who are the manufacturer of the film, in fact the granular product as well, that we source the product from them, we advertise that it's a Victrex product, and then they send referrals to us for people wanting small amounts of PEEK film. They do the same for the PEEK powders as well. And if you consider the range that we have, covers anything from 6 micron up to 500 micron in film, that's quite a decent range. And we also have the amorphous and semi-crystalline versions of this film, Active 1000 and Active 2000 being the brands. And again, a bit like the Kapton, it's a very reliable and consistent film. It's manufactured to some very high precision standards in terms of the control systems used in the film line. And I went there, been there about 3 times now to see the film line, and it's quite an impressive setup they have there at Fort Thornton Cleveland. up in Lancashire. It has a very high temperature performance, but not quite as high as obviously Kapton, and is rated to 180 degrees C for mechanical and 260 degrees C for electrical properties. However, bear in mind it does have a glass transition temperature of 143 degrees C. So you are seeing softening before you get to 180, which is why it's relatively flexible. The other thing to bear in mind with that glass transition temperature of 143 is that the amorphous material will actually recrystallize at around that point. So although you may start off with an amorphous polymer film, if you heat it above 143, it will then quite quickly recrystallize and become opaque, or rather cloudy, depending on the thickness. However, it's got good dimensional stability because of these high glass transition temperature. It's also very good wear performance. Low outgassing, we've seen that for use in a lot in things like semiconductor, and I do recall some parts being manufactured some years ago for laser inkjet printing, very precise inkjet printers going back sort of over 20 years. Another V0 rated material, and related to that, low smoke and toxic gas emission. So it's quite a performance material in its own right. Superb electrical insulation makes it ideal for things like, again, printed circuits, and there are a couple of examples here. Very good chemical resistance. So again, very difficult to characterize if you're looking at working out the molecular weight. Again, another one with high energy radiation resistance. So could be applications in space and in nuclear and things like microwaves even. It can be steam sterilized. So your food applications. So if you're food processing equipment, if you're operating at very high temperatures to sterilize food. Also, strange enough, also hot and cold water, although possibly not a big application when there are other competing materials. As we said, also suitable for use in clean rooms. So again, the low outgassing can be a real key in the use of PEEK. And in fact, my history, again, going back to Victrex of PEEK, I used to look after the product range back in the days when Victrex first sort of came out of the ICI. And it was one of the products I looked after. So I gave training programs on PEEK and Vespel to distributors. So it's taken me back quite a few years, actually. Then we'll look at what do we stock. Well, we have the semi-crystalline range from 8 to 500 micron, the amorphous range from 6 to 250 micron, and then a bit of a lonely one, a black version of 1000 grade, or the semi-crystalline grade, at 75 microns. And the little image here is of a speaker cone. Again, being a thermoplastic material, you can thermoform PEEK into a variety of shapes. Again, although quite high forming temperatures compared to other competing materials. Then we can look at one of the green products, and the reason that I've chosen PHP partly is because the history of this product goes back again, as I mentioned, ICI. My predecessor, a guy called Barry Saunders, introduced the product quite some years ago, and we found, because all we had at the time were a few film grades, a few examples of film and a few sheets, that just granules didn't really do much for us, and a bit of powder. So we looked at what can we do with this product. So we teamed up with a processor, and they managed to extrude some rods for us. Now, one of the things that we learned from that process about PHB is that it crystallizes extremely rapidly. It can be very brittle, and also being a product made by bacteria, we also found actually thermal stability, it didn't half smell something terrible when it degraded. So unfortunately, when the product actually came into our warehouse, our poor goods in guys were exposed to some pretty nasty smells when it first arrived. It was not nice at all. It's a polyester, so in terms of characterizing, probably easier than other polyesters like PET. What you actually get out of the reactors is not a viable thermoplastic. Pure PHB, you cannot process it. It has poor chemical resistance and is very brittle, as we said. So what you have to do is further compounding of other additives into it to make it a viable thermoplastic. One of the things that it also is, as it's a natural product, you will get other polymers, particularly polyhydroxyvalerate, will form naturally at the same time. And although we list it as PHB, you can get up, in theory, get up to 2% by weight PHB within that PHB. The PHB has an impact on its crystallization, so you tend to get slightly more ductile material as that PHB content increases. So we'll just briefly go through the way it's produced. So you've got bacteria in an aqueous media, which is munching away on the sugars that have introduced and into a fermentation process, and you get roughly 8% of all that mass is turned into PHB. So over 100 kilograms of PHB per meter cubed of fermentation media. It's quite an old process, goes back to the end to ICI, been around for a number of years, which the product was then sold on to Monsanto, and more recent years it's found a few smaller specialist manufacturers in the marketplace. Just to maintain those green credentials, as solvents are used during the recovery of PHB from that biomass, the solvent is recovered, and what you get out at the end of the process is basically a white powder, which at this point isn't a thermoplastic, and you couldn't really process it. You would basically find that it would degrade pretty rapidly. And here's an example of what PHB would look like under a microscope. Now, to make a viable product from this white powder, you would then look at pelletizing it through an extruder effectively. I don't know if anybody has seen the kind of compounding lines that have like a metal die or plate with lots of little holes, and you extrude lots of little tiny rods, typically about 3mm diameter. And whilst they're still quite soft, a metal blade comes down to chop them to length. So you get sort of anywhere 3 to 5mm long. The shape of those granules, as they are, can vary between batches because, you know, they're being cut by this blade, so they can be squashed. So when the people ask for consistent shape and size of granule, is very often you will not get that, you know, consistency. So during this compounding process, they add nucleating agents to, again, that's to aid crystallization, and plasticizers to again overcome the brittle nature of it. And also, which I've forgotten to put in there, is the nucleating agents are actually minerals, which, although are not a polymer, are actually friendly to the environment. So you're not putting nasties in there into our supposedly green material. PHB, I believe, for us is an area that we're seeing more recent growth. Cost compared to other thermoplastics is still fairly high, but with the drive to more sustainability and renewable resources, then PHB is an interesting product to have to bear in mind in the arsenal of looking at a broader solution to applications. Then finally, we can show historically how our polymers range, going back to our financial year 2001, that's 2000 to 2001, where we've seen quite decent growth, albeit from a low base, to possibly this year we're looking at around 1.8 million across the broad, the full range of materials, but with Kapton, with PEEK and polyester possibly making, well, definitely making some of the largest contributions to that sales growth. And really the growth has been down to having a very broad range, having new products being introduced fairly regularly, but also the ability to supply small amounts where perhaps going direct to the manufacturers or other distributors, you would struggle very hard to get small amounts of these materials. I mean, typically we're finding the minimum production volumes are increasing fairly rapidly, and some of them are going into the region of tons of material rather than, you know, a few grams and a few kilos. But hopefully, as I say, this gives a flavour of some of the products, far too many to talk about in a relatively short space of time, and I hope it acts as a starting point for a conversation that we can have going forwards, and feel free to contact me when you need any advice. Go through technical@goodfellow.com or info@goodfellow.com if you have any questions after our session. And I hope I haven't sent anyone to sleep.
No, you haven't. Thank you very much, Paul. Very informative presentation about polymers, and you have covered a great range. For me, at least, it was indeed very, very interesting. We have a couple of questions from the audience, so I will start with that, with the first question that we got. What is the difference between plastics and polymers?
Okay, yeah. So polymers are long chain molecules, and you can have naturally occurring polymers, as in like DNA. Plastics are also long chain polymers. So a plastic is a polymer, but a polymer isn't necessarily a plastic material. And I hope that makes sense.
Thank you, Paul. Is ABS a thermoplastic or a thermoset polymer?
Yeah, ABS is a thermoplastic. It stands for acrylonitrile butadiene styrene. Styrene being the amorphous bit, and you've got a butyl rubber to modify the impact. So yeah, it is a thermoplastic.
Thank you. Next one. Considering the insulating nature of polymers and high mechanical strength, can it be used to replace transmission towers carrying high voltage current?
Oh, that is a really good question. Yeah. Traditionally, I would say when you're looking at replacing metallics, there are a great deal of opportunities for plastics in general. A lot of work, in fact, in my time has been on replacing metallics. So I have to be careful because we don't want to do ourselves out of business, out of metallics business. A lot of things like carbon fiber reinforced polymers, glass fiber also. You could look at perhaps liquid crystal polymers. But I think in the area that you're talking about, probably the biggest opportunity is actually with composites. So you would look at, say, pultruded tubes or sections to compete with a metallic structure. The problem with thermoplastics would be being able to make those structures in continuous lengths. So you would have to have really things like, I say, a pultruded composite would probably be better placed.
Thank you, Paul.
Okay,
and last but not least question is, so can we use PEEK to make reusable Petri dishes instead of glass and a one-time use? How long will it last, since it has a TG of 140 Celsius degrees, almost near the sterilization temperature of 121 Celsius degrees?
Yeah, actually, I hadn't thought of an application like that, to be honest. Yeah, I mean, PEEK, very good chemical resistance, very stable. The 143 degrees C, you're starting to see softening, but not huge amount. So if you start with a semi-crystalline PEEK, yes, you could have a Petri dish. Yes, you could repeatedly steam sterilize it as well. So it would be a perhaps more robust product. So if you're worried about dropping a glass Petri dish, breaking it, you wouldn't have the issue with PEEK. It has a much higher impact strength. So yeah, although the downside with that would be relatively expensive in comparison, but if you get enough reuses out of that Petri dish, then you would start to see savings, yeah.
Great. And another one came in. Is it possible to replace all the polymers by biodegradable ones? Sorry.
Yeah, that's a very interesting question. I'm glad you've asked that. It's an area that I've personally been thinking about over a number of years. I can see that there are huge opportunities to replace a lot of traditional plastics materials with biodegradables, or in fact expand that further and look at materials from sustainable sources. So not necessarily when you finish with that product would you necessarily throw it into composting. There is still, I can suggest, a big role for traditional plastics materials, because if you think about a life cycle of a product, it's fine if you want something, for instance, say short life cycle, where you're looking at food packaging or packaging in general, that you don't want to have the concern of having to collect that material where you could put it in your compost. But for instance, if you wanted a durable product, like say, for instance, guttering on a house, you would want that material not to degrade in its life cycle. You'd want it to last for many, many years. So there is, I think, a place for both the traditional sourced materials, where they will not degrade under in the environment, but also I think there are lots of opportunities to replace traditional materials where I think we've been remiss in not treating them as a resource and collecting and recycling. So I think the longer-term answer is yes and no. There's a role for each in our future.
Thank you, Paul. Thank you very much.
Yeah, thank you.
These are my questions. Prasad?
Yeah, thank you, Dr. Aphrodite. I think we'll take the last question. That is, studies shows polymeric nanoparticles accumulating in human body. Is this something to be worried about in the future?
Yeah, it's funny actually. I was talking to a researcher from it was University of Southampton yesterday, who was looking for materials for marine environment, sort of looking at the impact of microplastics. And in fact, I have some history going back a few years to a meeting I had in Germany with the Fraunhofer Institute and the Norwegian Geotechnical Institute, where they're looking at the impact of microplastics in the Baltic and Oslo Harbour. Now, the thing to bear in mind, there's some conflicting stories that we're hearing about plastics in the environment. You hear about people saying, well, they're hanging around in the environment for many years. So you see some really shocking photographs of sort of like almost a raft of plastics materials floating in the sea. So they're saying it doesn't degrade quickly. Yet on the other hand, we're talking about microplastics, which have degraded relatively quickly. So some of the microplastics, I believe, come from beauty products. So opacifiers, I think that's the right word, but also scrub agents as well. There also is the opportunity that some of those plastics materials will come out through degradation in the environment. Say, for instance, PVC will break down fairly rapidly. But I think there's a bit of conflict between where is this actually coming from, and I think even researchers are finding it difficult to understand exactly where that product has come from in the life cycle. But it is good that we are more aware of the potential, and that people are taking it a lot more seriously. But it's our behaviours that need to change, not necessarily the materials themselves. Sorry, that's a personal view.
And another one. Thank you for your questions. I'm sorry, Prasad, I didn't see the previous one. Hello. Does Goodfellow provides ingredients for light diffusion for polycarbonate sheet extrusion?
Yeah. Actually, I have some personal experience with this. Not actually with polycarbonate, but with acrylic. We had an application for a profile that used in the rotating banners used in airports. And we hadn't realised that with LEDs, they have such a focused light source that any of the striations caused during the extrusion process were causing fingers of light to come through. And the way to overcome that is to have, I don't know if you've heard of glass ballatini balls, which are tiny little glass spheres. And you can get these grades already compounded with those spheres in, or you can actually buy tiny glass spheres, soda lime glass, borosilicate glass in these little spheres, which can be compounded into plastics. And being spherical, fantastic for compounding. So you're not smashing them up like you do with glass fiber. So yeah, you could definitely do that.
Excellent, thank you. Do we have any other questions? Prasad?
Yes, Aphrodite, we have two more questions. One is, can polymers be printed on? And the second is, how can we as a society compensate the damage done to the environment by the plastic?
Right, yeah, printing. There definitely can. Now, the key characteristic that you're looking at is a thing called the surface energy. With a lot of plastics materials, if you go for, say, for instance, polyethylene, it has a very low surface energy. So for materials like that, you would need to either chemically prime them, or you need to use something like a corona discharge or a plasma. And those two techniques, really what they're doing, or in fact all three, is to try and introduce oxygen into the surface and raise the surface energy. Now, there are materials that can be directly printed without having to have some of those techniques used. However, the key is trying to balance your surface energy, your ink, to the surface energy, or rather match the surface energy of the polymer. So it's a bit like if you're trying to bond. Generally, you would have to try and match the surface energies to cause the ink to adhere or to spread on the surface, so it stops it from beading. Again, the environmental question, I think I heard you right, is how can we mitigate the impact of polymers in the environment? Well, firstly, recycling, collection, our attitude towards those products. We can increasingly look to biodegradables for the correct applications. So for instance, I'd say packaging, or where the infrastructure of collecting waste is difficult to establish. I mean, in the UK, we put our bins out for recycling, but a lot of that doesn't actually end up being recycled because of the issues of contamination. It's very difficult. You could look at putting things like degraders into them so they break down, but again, you have the issue of what happens to the bits that break down. So there's I think there's a number of approaches that need to be taken. Consider plastics as a resource. Be more careful about how you dispose of your plastics materials, whether it's a drinks bottle or a sandwich pack or cling film. Be more accepting of the fact that you may have to use different packaging materials. Go back to, I mean, I can recall as a child having paper bags for your shopping. You would have Hessian bags. You would go to the shops with a bag rather than expect the shop to give you a plastic bag. So I think a lot of the gains to be made are from our own approach, our mindset, and basically looking after the planet, because we only rent it from the future generation. So let's be kind to it. I hope that's
Yes.
a good answer and my personal opinion.
Thank you, Paul, for such an exciting and detailed discussion on polymers. I'm sure it has added a great value to all our participants who joined today for the webinar. And huge thanks to all of those who joined. Thank you everyone who asked the questions, a very interesting one. And also feel free to reach out to us if you have any questions, and we will get back to you with the answers. Thanks again for Paul for taking time out from your schedule, for our Indian researchers today. And I also thanks to my colleague from Merck India and Goodfellow. Now I would like to request Dr. Aphrodite for the closing remarks from Goodfellow, please.
Thank you very much, Prasad, and the Merck team for hosting and organizing this interesting webinar. Goodfellow is glad to collaborate with knowledgeable partners as yourselves. And as my colleague Paul mentioned during his presentation, Goodfellow is unique in offering a comprehensive range of polymers, metals, alloys, ceramics, glass compounds and composites, and other advanced materials to meet the research, development, and specialist production requirements of science and industry worldwide. As researchers and industry sectors explore the fascinating world of materials, there is an ongoing requirement for continuous improvement and innovative solutions in numerous applications. Goodfellow is actually following these trends very closely and brings to our customers the best quality and leading-edge products, while at the same time is providing free delivery in extensive range of stock range of over 70,000 products. This spans in 48 hours, and there is no minimum order quantity for our catalog products. In addition, Goodfellow is offering customized products and free technical support, as Paul has mentioned before, by engineers and scientists. For the technical support, please send your emails to technical@goodfellow.com. Thank you very much for listening to our presentation, and thank you for your time as well.
Thank you, Dr. Aphrodite, for your closing remarks. And I once again thank you all for attending this webinar. Hope to see you all soon. Stay safe and healthy. And those who are still working in lab, please take care. Thank you very much.
Thank you.
Thank you.